Dear Mr. President of the Académie des Sciences, dear Mr. President of the CIPM, dear CIPM members, dear delegates from all over the world, dear guests, thank you very much. This is the CCU presentation, the Consultative Committee for Units, which was founded in 1967, only a few members around. This was our last meeting where we finally recommended the revision of the SI to the CIPM. Our task is to provide advice about units of measurement, to develop the international system of units, and to prepare the SI brochure. We have 15 members, among them 11 members from the National Metrology Institutes. We liaise with 3 international unions, with 5 intergovernmental organizations and committees, and with 5 international commissions and committees. So we form a global forum for progressing the state of the art. It's actually the only global forum for units. We are facilitating the dialogue between NMIs and all stakeholders, and we seek always consensus. And so we underpin global comparability of measurements. So let me first remind you what a measurement really is. You go to the supermarket and you buy 10 kilograms of tomatoes. A runner runs at a speed of 55.4 seconds, needs a time for a certain distance, and you are going with a speed with your car with maybe 87.4 kilometers per hour, where you was only allowed to go 50 and you're in trouble. So you see a general scheme. Any quantity you can measure, any value of a quantity you can express as a number in terms of a unit. And for the mass, we have the unit, the kilogram, which still is the artifact sitting here in Paris. For the second, for the time, we have the second. And if we go to a very small pendulum in an atom, in a specific atom, cesium-133, this pendulum is extremely fast. It has more than 9 billion oscillations per second. And one important concept of measurement and metrology is that you always give an uncertainty to a number which you measure. Now, in this case here, this is a constant of nature. And then you could decide that you say, okay, maybe I define there's no uncertainty, and defining the second by saying that a second is exactly 9,192,631,770 oscillations of this little pendulum. And this is how you define a unit, by fixing the numerical value of a constant of nature. And this was actually proposed by James Clerk Maxwell early on, when he said, take the properties of atoms, not those of the Earth, to define units. Now, in the present SI, we have artifacts like the kilogram, we have material properties like for the Kelvin, measurement prescriptions and defining constants. And in the future, in the revised SI, we will now consequently go the way through defining constants. So the SI is a system in which the hyperfine transition in the cesium-133 atom is exactly 9,192,631,770 Hertz. The speed of light c is exactly 299,792,458 meters per second. The Planck constant is exactly h equals 6.6260715 times 10 to the minus 34 joule seconds, and so on for the elementary charge, for the Boltzmann constant, for the Avogadro constant, and for the Luminous efficacy. So this is a system. So in the old SI, we defined units and measured constants of nature with some uncertainty. In the revised SI, we fix the numerical values of defining constants to define the units. And then we use the equations of physics, and we use defining constants to realize the units in general and the base units in particular. This is based on our present understanding of nature. It is valid for all times and civilization. It is throughout the universe, and this was the expression of Max Planck, very visionary in 1900, when he postulated the Planck constant and to explain the radiation law. At the end of his very famous paper in 1900, he was writing, With the help of fundamental constants, we have the possibility of establishing units of length, time, mass, and temperature, which necessarily retain the validity for all times in civilization, even extraterrestrial and non-human. And this is what we are going to do. Nevertheless, this was a vision, a theoretical vision. We have to bring it into practical relevance. And this was done by two seminal papers in 2005 and 2006, setting the scene. And some of the people who wrote that are here. These are Ian Mills, Peter Moore, Terry Quinn, Barry Taylor, and Edwin Williams. So we have to give them a lot of credit, actually, because they paved the way to form a practical system of units on this basis. And I would like, actually, together with you, if you are here, for a little celebration in the next break. Now, this caused many recommendations, the first CIPM recommendations, several resolutions of the CGPM. It took us 13 years, 7 CCU meetings, and actually I'm very grateful to my predecessor who really advanced that very strongly, Ian Mills, and unfortunately he cannot be here today. And this brings us, this long, long way brings us to resolution 1 of the 26th CGPM drafted by the CCU, which you, the delegates, are going to decide today. As we all know, this is a global decision because we have 102 members in the associated states. They form 98% of the world economic power. We are defining a global measurement infrastructure, and as we heard several times this conference, this is a cornerstone of international quality infrastructure. Now, how does it work? How can we use the equations of physics and combinations of defining constants to realize the units in general and the base units in particular? And I'll show you the examples. Now, I've said already for the time, we need to fix the numerical value of a pendulum, of the oscillation frequency of a pendulum in an atom. So what we do is we generate an external radio frequency. We stabilize this frequency to the atomic frequency via, for the specialists, the separated field Ramsey configuration. So in these apparatuses, so-called fountain clocks, we shoot atom cloud up into the gravitational field of the Earth. They are falling down. They are passing twice a resonator. And by that, we can realize a second with a relative uncertainty of 2 × 10⁻16, 1 second in 160 million years. And this is not just for fun, it is for GPS, it is for net synchronization, it's for science, you need it every day. Now for the meter, we need a second constant, which is the speed of light, where we fix the numerical value again. So how can you realize the meter? Here's one example. You're on the Earth, and here's the moon, and there's a mirror on the moon, which was mounted by the Apollo 11 crew in 1969. So you can shoot a laser up there, it comes back, and it has a travel time of 2.656 seconds about. So we can use this very simple equation that the distance from here to the moon is just the fixed numerical value of the speed of light times the time you have measured, which gives you about 384,000 kilometers. So this is a realization of the meter based on this definition. For the kilogram, it's a little bit more difficult. We need actually 3 defining constants, most notably the Planck constant. And we have 2 methods for macroscopic masses to be realized. The first one is the so-called silicon route, the silicon sphere, where you count the number of atoms in the crystal sphere of enriched silicon-28, and these fixed numerical values of the constants, together with some other theory behind it, basic quantum mechanics, gives you a mass scale for it. So this is the equation. So the mass of the whole sphere is given by the number of the atoms. It is given by the mass of the electron, which is given by a fundamental quantum mechanics and these defining constants, and the ratio of the electron mass to the atomic mass of the atoms in the sphere. So essentially, you can see, you can kind of cancel out the electron mass, and then it becomes very simple, namely that the mass of the sphere is just the number of atoms times the mass of the atoms. We have a second method, which is a so-called Watt balance or Kibble balance, very complicated, sophisticated experiments, which will be explained by the president of the CCM, I think. So in this is a balance where you weight the gravitational force with the electromagnetic force. And in this equation, again, the Planck constant and the others are also actually needed. And as I said, this will be explained in detail a little later. For the electrical quantities, you fix the numerical values of the electron charge. And then it's very simple. If you would have such a device where this blue little ball is an electron, and you switch this potential, you can just count the flow of electrons in a second. So the current I is given by the well-defined charge of the electron times the number of electrons in a given time. So this sounds very simple. It is very simple conceptually, but technologically it's high-tech at the end of the day, because you need these kind of quantum dots. This is one of those here at the beginning. Then you shift one electron through, you detect it on this detector, then you go to the next pump and so on to make some error corrections. And finally, however, you can define the ampere by just counting electrons in a given time. Here it's very instructive to see that you could also directly realize other quantities, not only the base quantities like the Coulomb. For that, you would only need to count electrons. Or in the electrical quantities, you can directly realize the ohm and the volt by the von Klitzing and the Josephson effects. And we will hear about that later by Klaus von Klitzing. Let us come to the Kelvin. Again, we need three defining constants, most notably now the Boltzmann constant in addition. So now we have many different equations to realize the Kelvin. The bottom line, however, is that energy is proportional to temperature. And this was shown in this very beautiful experiment by James Joule, where a mass m in the gravitational acceleration g falls down a distant x. And this energy is transferred to a squirrel in this little container and gives rise to a temperature rise. Microscopically, this means that the molecules in this container of mass m would increase their mean velocity due to this interaction with the squirrel. So for an ideal gas, we have the relationship that the mean kinetic energy in this gas is proportional to the temperature, and the proportionality factor is just the Boltzmann constant. And with that, you can realize the temperature. For the mole, we just only need one constant, the Avogadro constant. As everybody knows, two molecules of H2 and one molecule of oxygen gives two molecules of water. This is on the atomic level, but chemistry is not on the atomic level, it's on the macroscopic level. And so you have to multiply with a large number, namely the Avogadro number, 6 times 10 to the 23 entities. This brings you to the macroscopic level. If you now divide by the Avogadro constant here on top, this brings you to the macroscopic level within the amount of substance concept. And this is what the chemist then can really need. They take 2 mole of H2 and 1 mole of O2 and get out exactly 2 mole of water. So with where 1 mole contains 6 point something, 10 to the 23 specified entities of atoms and molecules. And finally, last but not least, the candela, where we fix the numerical value of the luminous efficacy. So the sensitivity of your eye as a function of the wavelengths or the color of light depends on the color of light. This is a luminosity function, and it is different actually for day-night and night light. And you see these two curves cross at exactly one point, 555 nanometers, 450 terahertz. And by fixing the numerical value of the luminous efficacy, this translates then to a fixed numerical value in terms of spectral luminosity, luminous efficiency, efficacy, of exactly 683 lumen per watt. And some people say that KCD brings humanity into metrology. Now, these were some examples, and you could have many other equations, many other examples how we can realize the units by fixed numerical values of defining constants. So it's a completely new concept. It guarantees long-time stability because the constants cannot fall down, they cannot be scratched, they will just be constant. It is usually a set of defining constants establishing the units in general, like for the candela, like for the kilogram or the Kelvin. We have different realizations. So we can do key comparisons. Things are getting safer, less correlated. We can realize everywhere, maybe in the universe, maybe not at the very end of the universe and in a black hole, but in most parts of the universe, as envisioned by Max Planck. So we don't need to go to Paris anymore. Sorry for that, but actually we love to go to Paris, and we are sorry about it. Often we can realize throughout the entire scale, and this is actually also true for, especially true for the Kelvin, where we have many, many different equations: acoustic Garth thermometry, dielectric constant Garth thermometry, Doppler, noise, radiation thermometry, all of that can be used. Base units, as I've been showing to you with the electrical units, are only a convention, because we can directly realize the ohm, the volt, the coulomb, and the ampere. Electric units are back in the SI, very, very importantly. So we have a coherent and a consistent system based on our present knowledge of nature. This consistency can be ensured, for instance, by the agreement between values between the silicon kilogram and the watt balance, and we can do other experiments to ensure that. Very importantly, whenever we do a better experiment, whenever we have a better technology, we have a better realization. We are not limited by the definition. So the ultimate precision you could get for counting the numbers of atoms in a silicon sphere would be on the level of 1 atom. And that will bring you to a relative uncertainty in the order of 10 to the minus 26. If you count individual electrons for the ampere, this will bring you to a relative uncertainty of 10 to the minus 19. So we are only limited by the quantization of nature. We are not limited anymore by our definition, so we are completely open, technology open for the future. So this is obviously a huge change, but it shouldn't be a change for everyday life. So we have to make sure that there is continuity, there is harmonization and stability of the new system. And in order to do so, we had to make sure that the constants, the value of the defining constants, that those are measured so accurately that in the future they can serve as an accurate realization. And there has been requirements from the different CCs actually, and these requirements were all fulfilled. So the relative uncertainty for the electron charge is in the order of a few times 10 to the minus 9. The relative uncertainty for the Boltzmann constants, a few times 10 to the minus 7. And the relative uncertainty for the Planck and the Avogadro constants is actually 1 times 10 to the minus 8. And this actually is fine. Everybody agreed. All the CC requirements were fulfilled so that we now essentially can go ahead to realize. So ladies and gentlemen, I think, dear delegates, I think this is a historic moment in time today. It is a millennium-long effort of mankind to establish units of measurement that will come to an end today, I think. It started with artifacts like several thousand years ago, like for the volume, the length, or for the mass. And it ends up with the most abstract concept which we can think of to define units, which is sometimes also called the quantum SI. As I said before, this will be valid for all times and civilizations. It will be valid throughout the universe, as envisioned by Max Planck, but supported by many, many, many ingenious researchers, and some of them, which partly give the name to the constants, are listed on this slide. This will underpin what we sometimes today call the second quantum revolution. It will underpin innovation in science and industry for the benefit of mankind. And at that point, I really would like to thank for the last 4 years of collaboration with many, many people, with international organizations, with NMIs. It was often hard discussions to come to a consensus. But at the end of the day, we had this big vision that we have to do that, and we reached consensus. And I think this is really a good sign for the future of mankind. We, at least the Media Convention, one of the first contracts, international contracts ever, we could demonstrate that we can come to common decisions, that we come to a consensus, that we go forward, that we shape the future, and I hope other international organizations and countries would go the same way. Thank you very much for your attention.